All right, so the first thing I want to do is actually make a solenoid. And the solenoids we've seen class so far, they're the ones with the enameled copper around an iron core. Okay, those are really hard to change. They're made to be a solenoid that's very precise and doesn't change. And I want to do the exact opposite. I want to be able to change my solenoid. And from an old AP question, actually, I came up with the idea of using a spring as a solenoid. Now, this spring, we've labeled it with some smiley faces. They're thunderstorms today. Ooh, they're happy. But for really, we want to use spring because I can stretch it, and I'm changing the number of turns. And your first thought might be, Mr. Nendick, okay, this is made of metal. It's going to conduct through here. There's no enamel coating. There's no insulation. That's true. But in this case, if you look very, very carefully at the spring, and we'll see if I can't find the camera. Here we are. It's oxidized. It's got a coating on the outside of it from kind of it being exposed to air. And the shiny metals on the inside, so actually the resistance on the outside is pretty high. It actually acts really nicely. It is insulated. And so what I'm going to do first is say, okay, well, this is a spring. And so I need to consider that with my formula, which of course is mu naught times n over L times I. Well, I need to know how long my spring is, so I just take a meter stick and I measure him up and butt him up, and he looks like 19 centimeters long, but that actually doesn't matter to me, because I'm not going to count all the coils in this spring. That's a waste of my time and yours. What I do instead is count the number of coils in a small amount, and then just turn it into coils per meter. That's easier to work with the math anyway, because then I can just put a 1 in the bottom of the equation. And so here I've got a centimeter of this apart, and I see 1, 2, 3, 4, 5, maybe 6. Let's go with like 5.5. We're making an approximation here. So I think there are like 5.5 turns of this spring per centimeter. So I'm going to go ahead and take that down in my notes. And I say, well, n equals 5.5 per centimeter, or if I do that per meter, then I need 550 turns per 1 meter. And that makes pretty good sense to me. And then the next question is, well, what kind of power do I have? Okay, if my equation is mu naught times that ratio times I, I'm going to need what kind of current can I pass through there. So the next thing I'm going to do is measure up the current of my power supply. So let's hook that up and take a look at it. All right, so what I want to do is I want to start off by taking a look at solenoids. And mathematically, solenoids are actually pretty easy to deal with. The magnetic field, B, inside of a solenoid is going to be equal to mu naught, which we learned about yesterday, times the ratio of turns in the solenoid divided by its length times the current I through it. So I have always the same number, 4 pi times 10 to the negative 7th with all those weird units. I have the turns per meter, and it's got to be in meters, of course, because of my units, times the amps. And that's going to be the magnetic field in a solenoid. And actually, that's really pretty straightforward. After all, mu naught's not going to change. I is pretty easy to control in a circuit. And n over L, that's just a property of the solenoid to start with. The math here works out pretty nicely. So when we're working through this guy, actually, all we really need to know is about the physical properties of our solenoid. And what I want to do today is do a couple experiments with a simple solenoid. In this case, we're going to be using a spring. And because of how this video is going to be made, let me just kind of pre-elect the experiments here for just a minute. So on to a new slide. So the first thing we're going to do is we're going to take a solenoid, which is going to be our spring, and we're going to measure that N and the L and the I going through it, and we're going to measure and predict the magnetic field and compare it to our results. The second thing we're going to do is we're going to take that spring and we're going to stretch it out and see how it compares. And the next thing we're going to do after that is we're going to try to set up an oscillation. So we'll have a ground, and we'll have a hanger, and we'll hang the spring with a mass on the bottom. And of course we know this will have a rest position, and it will perturbate up and down. And I'll have a Hall effect sensor in the middle of it that can measure the magnetic field. And we can see how compressing and expanding the solenoid, which is to change the turn ratio, how that's going to end up actually affecting this all. So that's really the first game. All right, so here's the next step. I've set up a simple power supply here. It's a bit old, but it's variable. So if you come down here on the bottom, it says I can get about 12 volts up to 7 amps. I need to know exactly how much I'm getting though. And so what I've done is I've wired up an ammeter. Just going to measure my amperage. And that's in series. And on the end of it, I've got some alligator clips. What I'm going to do here is I'm quickly going to just clip this up. So hold tight with me for 30 seconds. And there we go. So I've got the spring hooked up to the power supply. There's a complete circuit and an ammeter here. What I'm going to do is I'm just going to figure out how much power I can put through this. So I'm going to start turning the power up, and you can see there's half an amp, there's a full amp, 2, 2.5, 3. Looks like I max out around 4 amps. Let's just choose a nice round number. Let's just say like maybe 3 amps there. It's an easy number to work with. Okay, so there's now 3 amps of electricity, 3 coulombs per second passing through my spring here. If I touch the spring, I can feel that a little bit as like a tingling. It's also very warm. The spring would heat up, I don't know, to a couple hundred degrees within a minute because it's got a relatively high resistance. It's not an ideal conductor by any means, but it's going to work for our experiment. So we know we have to go relatively fast when we're doing it because otherwise the resistivity of the wire is going to change and the current is going to change as it goes through there as well. But for now, this is working nicely, so let's go ahead and solve the equation. Get fast. Alright, so again, the magnetic field in a solenoid, that's B, is equal to this mu sub naught term times the ratio of turns divided by the length times the current through it. We've set this up now. We know everything going on here. B is going to be equal to 4 pi times 10 to the negative 7th meter Tesla over amps. We know that we have 550 turns per 1 meter, and we have a current of 3. So I get what? 1650 times 4 pi times 10 to the negative 7th, which is going to come out with a relatively nice number. All right, so here's the setup, and what I'm going to do is I'm just going to insert the Hall effect sensor directly into the solenoid, into the spring here. Focus that a little better. And I'm going to just run current through it. And the first thing I do, and as I do that, I'm just going to run that current through, and I'm going to change the, oops, let's flip this around here for a moment so the numbers are positive. I'm going to change the amperage and bring it all the way up, and bring it back down. And then the second experiment I'm going to do is I'm going to do that same thing when it's at a constant aperture, and I'm just going to go ahead and stretch the solenoid out and back and forth a little bit. It's hard to do with holding the iPad, so we'll be looking at the screen of SparkView anyway. And so what I'm going to do is I'm going to stretch this spring out and watch the magnetic field first change. The first thing I want to do, though, is check and make sure that our prediction's right. Remember, we predicted the 26 Gauss magnetic field in there. And so what I'm going to do is bring this up to 3 amps on SparkView, and we'll see if we get something in the neighborhood of what we predict. All right, so I've got SparkView up here and running. I've got that apparatus, and I'm going to first just set up a simple chart. And so that chart I'm going to set up here is just a normal counter, and we need to measure in Gauss. So let's set that up. Remember that Gauss is just 10,000th of a Tesla. Okay, so I've got that up and running, and right now, of course, the magnetic field is 0 because I'm not reading. So I turn it on, and my magnetic field registers 1.14 Gauss, which is probably just background from the Earth, right? We said that should be in the neighborhood of 0.5 Gauss in reality, and I just slid the Hall effect probe further into the solenoid. All right, now what I'm going to do is I'm going to take this, and it's a relatively noisy reading, and I'm going to go ahead and just start putting current in. So there's 1, 2, and 3 Gauss right there, 3 straight up. And our prediction was 26 Gauss. And right now we're measuring 25.7, 25.8. Okay, it's going up. Why is it going up? That's not right. What's happening here is my wire is heating up and the resistance is changing, and how the current's working to compensate for that is the problem. So what I do is actually just keep it here at about 3 amp And we're just going to turn it off really fast and go back to 0. And I'm just going to let the the solenoid cool radiatively here for a few moments. And watch what happens when I turn it on just right up to 3 here real fast. All right, we're at 3 now. 24, 23. Okay, and one more time. We're at 3, about 23, 24. Okay, so we're in the neighborhood. We're not exactly where we're at, but we're close. And that's just the limit of our experimental setup. I mean, we're using a spring as a solenoid. That's not perfect. The next thing I want to do is come over here and stop this thing recording. And I'm going to go ahead and hit no and go home and build up a graph. So here we are. I've got this thing here. Still measuring. I'm just going to build a graph. And my measurement, let's put it still in Teslas. Okay. And what I'm going to do now is start graphing. Go ahead and fit the graph's data here. It's going to start increasing the current. That's 3, 3.5, 4. That's 4 amp. And you can see I have a nice stair-step function. As I start turning it off, you can see I can decrease the magnetic field by just decreasing current back to 0. And anywhere in between, I can get there by just changing the amount of current going through here, which is important because that means our equation, that I term, is going to actually help us understand what's going on here. This is about half an amp, and it seems to put out about 6 Gauss. And again, the reason why it's not exactly constant when you see this line dropping here is because this wire is getting quite warm. To the touch here, it's well over 100 degrees, probably pushing 150 degrees. And so we have to be careful with the setup. It doesn't last forever. Now I do have one more thing I want to show you, which is what happens if I try to make this a periodic thing. What happens if I try to expand and contract the spring? So the first thing I do here is pause the data. And I'm going to get rid of the data point here and start taking new things. And here we go. I've got a magnetic field. And what I'm doing right now, I've got my hands on the spring. And you can see it's not really changing from what it was. My hands are off here. And I'm going to just start pulling the spring. And the magnetic field, you see it dropping way down. And now I'm bringing it back together. And it's back to where it was. And way down again. This says I've stretched the spring to probably 3 times its normal length. Now I'm probably 4 times its normal length. And you can see I'm down here. Now I'm struggling to hold it between the warmth and the string's pull. So this is about the limit for how far I can stretch it. Even as it is, my data here isn't exactly clean. But you can see I'm varying the magnetic field by doing nothing more than expanding and contracting the spring. And of course what I'm doing here is I'm changing the number of loops per meter. I'm changing that N over L term of the equation. Now, I'm not doing anything right now to the magnetic field, and yet it's falling very, very nicely. That's, of course, a result of this thing getting quite warm, to the point where I'm going to have to turn it off and let this sit for a minute. All right, and here's our last little demonstration. So I've got that Hall effect sensor there in the spring or solenoid, and still connect up to our power supply and our ammeter. And all I'm going to do is I'm going to run a constant current through there. Again, that same 3 amps. And I'm going to put a 500-gram mass in the bottom of it. And when I do that, it's going to oscillate up and down, just like you're used to seeing from the labs. You know, the spring is going to woo, back and forth, right? We're going to do that. But we're going to do that and look at the graph of the magnetic field. And of course, what you're going to actually be doing is seeing the magnetic field change from the contraction and expansion of the spring in a predictable, repeatable way. Recording now. So I'm just going to come over here and start up a graph of the magnetic field. I don't care the units it's in Tesla, so I'm really just interested in the shape here. And here's our old data, so I can cancel that off, which I can't do with the screen. And I can start recording some new data. And right now the magnetic field should be 0 because there's no current, and it is. So I turn that current on, and you can see the magnetic field coming up near the 20 Gauss that we've been measuring. I'm just going to attach the mass and start it oscillating. Oops. You can see the data is nice and tight, so we'll have to fit it to the screen. And it dampens really fast. So I'm going to stop the data recording and fit the data to the screen. And you can see this nice up and down pattern when the spring or the solenoid is opening and closing. So that loop spacing has to be an important factor to us understanding why the magnetic field exists like it does.